Well, hello and welcome to Doc Onco Physics. Keith Onco here. Today what we want to do is we want to take a look at Newton's laws. Back in the 1600s, there lived a guy named Isaac Newton, probably one of the most brilliant scientists who had ever lived. And he came up with a variety of different things. He invented calculus, but he came up with three very simple laws called Newton's laws of motion, and they govern most of the things that occur for us on a daily basis. And what we want to do in this session, actually this is session 1 of the Newton's laws lesson. I'm going to break this up into 2 different sessions so it's not too long. We want to cover these laws, and we want to solve some problems using the laws so that you can see just how we use his basic simple laws to solve a lot of different problems. So the laws that he has, there's 3 of them, all right? And the laws, first of all, are, the first one up here, is that an object at rest will stay at rest, and an object in motion will stay in motion unless acted on by some unbalanced force. So it's easy for us to see or theorize or contemplate that an object at rest is not going to begin moving unless a force acts on it, all right, some unbalanced force acts on it. That's pretty easy for us to imagine. But in life, what we see, what we notice, what we observe, are that things that are in motion tend to slow down. Okay, and so our immediate thought would be that it takes a force to keep them going at a constant rate of speed or velocity. But the fact is that once an object is in motion, a force is going to have to act on that to change its velocity, to slow it down, to speed it up, whatever it might be. Okay, so say for instance I'm going to throw a baseball. Well, the baseball tends to slow down over time. What slows it down? Well, the force due to air resistance. Okay, if I slide a block across the table, right, the block starts out at a certain velocity and then comes to rest eventually, right? What slows the block down? The force of friction acting against the motion of the block. So Newton's first law is that an object at rest will stay at rest, an object in motion will stay in motion unless acted on by some unbalanced force. The only way it will change its velocity is if some force acts on it in some direction. Okay, so that's the first law. There isn't an equation associated with the first law. Right? It's just a concept. Right? Law number 2. The acceleration of an object is directly proportional to the sum of the forces applied to it. This is the law that has an equation associated with it. And the equation is over on the right-hand side. I just drew an arrow on it, right? The left-hand side is the sum of all the forces on an object. Well, if I have an object, and say the object is some kind of a cart or even a car, right? And I want to push that car, I can push on it myself, right? Just one person pushing on it, and that might be one force that's being applied to it. But what if the car is quite heavy, and most cars are pretty heavy? Right? So I might gather up a friend and say, hey, okay, you push on one side, I'll push on another side. Now we've got 2 forces, hopefully pushing in the same direction. But if we had 3 people, right? One in the middle, one on each end, we got 3 people, 3 different forces. Well, the left-hand side here is the sum of those forces, okay? And those forces can be pushing in the same direction. I could have one pushing in from the left and one pushing from the right against each other. It doesn't make any difference, all right? But what I want to do on the left-hand side is gather up all of the forces, right, in each dimension, all right, and then sum them up. And it's important here that we gather up the forces in a particular dimension, because when we write this equation, we can write one for the x dimension, right, and one for the y dimension, and we never mix them. Okay, we never mix forces in a particular equation. So I can't write one equation and have x forces and y forces in there and try to sum them up algebraically. It doesn't work. Okay, so we could potentially have two of these equations, one in the x direction or x dimension, one in the y dimension. Okay, so it says the acceleration of an object is directly proportional to the sum of the forces applied to it. So the left-hand side, what we do is we just take all of the sum of all the forces. That's what this funny symbol is here. That means the sum of the forces equals to the mass of the object, and we're going to assume that the mass doesn't change, times its acceleration. Well, if this is a linear equation, all right, if I change the force over here, right, if I double the force, what's going to happen to the acceleration? It's going to double. If I triple the force, the acceleration is going to triple. Right? It's a pretty simple equation when you look at it. Okay, so that's Newton's second law. Newton's third law, okay, is that for every action or force, there's an equal and opposite reaction or force. Okay, and some examples I have down here. All right, here's one example here of a swimmer. So the swimmer has come to the end of the lane, and the swimmer turns around, and now it's going to kick off of the wall. Okay, so what's the swimmer doing? Well, the swimmer's feet are applying a force to the wall. Okay, so the feet are pushing on the wall. What's the wall going to do? The wall is going to push back on the swimmer's feet. Okay, why does the swimmer then move to the left? Because the wall has applied a force to the swimmer's feet. Okay, what's one of the critical things about this is to realize that each one of these forces, this force here and this force here, are not on the same object. Okay, this force over here is a force on the wall. Okay, this force here, whoops, I want to do that. This force here, whoops, is on the swimmer. So there's only one force on the swimmer, and there's only one force on the object, on the wall. But because there was a force applied to the wall applied an equal and opposite force to the swimmer. Okay, and that's the third law. Over here on the lower right-hand corner is another example of that. If I take my finger and I push it against the wall, what does my finger feel? Well, it feels something, right? And the reason that it feels something is because the wall is pushing directly back on my finger, right? So it's trying to compress my finger, right? So here's one force, right? And here's the other force. But notice that each one of these forces is on a different object, right? The force applied by my finger is on the wall. The force applied by the wall is on my finger. So there's only one force applied to my finger, and there's only one force applied to the wall. We can write an equation for this as well, right? And it's down here. And basically what it says is the force on object 1 due to object 2 is equal in magnitude to the force on object 2 due to object 1. That's what these subscripts are for. The subscripts are simply labeling. I'll say this is object 1 here, and I'm sorry, I've already got them labeled over here. This is object 2, this is object 1. So the force on object 1, which is the wall, due to object 2, which is my hand or finger, right, is equal in magnitude to the force on object 2, my hand, due to object 1, which is the wall. Okay. Now, to be correct, I should add a sign in here, because while the magnitudes are the same, the directions of these forces are opposite. Okay, and it's critical to understand that. So that's Newton's third law. An example of Newton's second law, as I mentioned, the person pushing the car, right? Here's a person pushing the car over here, applying a force to the right, right? The car has a mass of 1,000 kilograms, and we might like to know what the acceleration is. Well, in a little while, we're going to actually solve a problem similar to this. Okay, so this is where Newton's second law would come into play. Okay. All right, so those are basically Newton's three laws. They're fairly simple, but we can apply them to a whole variety of different types of problems. And they're not always as simple as the person pushing the car over on the left, right? They can get, as you can imagine, much more difficult, right? Because not all forces are in the x dimension, all right? We can have forces in the y dimension. We could have forces, say this person was not pushing horizontally, but this person was pushing at an angle, okay? Then we have components of a force, like this, right? We have components, right? We have a component in the x direction, a component in the y direction. So we might have an F in the x direction and an F in the y dimension, all right? And we have to deal with all that, right? So it does become a little bit more complicated. But if you follow the rules that I'm going to set forth, you'll be able to solve just about any type of problem. So what type of forces are we going to analyze? Well, in actuality, in the world, in the universe, there are only 4 types of forces, right? The first type of force is gravity. Okay, we experience gravity each and every day. When we get out of bed, our feet hit the floor. All right, when we walk, our feet stay on the ground. Right, gravity is pulling us towards the center of the earth. So that's the first type of force that we experience. The second type of force is called an electrostatic force. All right, and the electrostatic force is basically the forces that interact between molecules and atoms that hold things together. Okay, that's the second type of force. You probably learned about that in chemistry if you've taken chemistry. Okay, third type of force is what's called the nuclear strong force. All right, and when we get into nuclear things much later in the course, we'll get into that. And the fourth type of force is the nuclear weak force. And we don't deal with that too much in general physics. Those are the 4 universal forces that exist in the world. Well, you might ask, well, wait a minute. What about the forces that we're going to deal with now? Because the types of forces that we're going to analyze using Newton's laws are gravity, right? Well, gravity is certainly in here. A push or a pull. Well, I don't see push or pull in the left-hand side of my screen here. I see electrostatic, nuclear, and nuclear. So believe it or not, a push or a pull is really due to the electrostatic forces between objects, right? When I push on something, right, the reason that the object feels my hand is because of the electrostatic forces, right, in my hand, in the object, right, and the interactions between those, okay? But as far as we're concerned, all right, for analyzing Newton's laws, we're not really going to deal with these guys over here. We're going to deal with these forces here, right? Gravity, a push or a pull, and friction. All right, those are the types of forces we're really going to deal with. So gravity, I think we're kind of familiar with. There's an equation for gravity. We'll deal with that in a little bit. What's a push? Well, I think we're all familiar with what a push is. Over here, we have an example of someone pushing on a door, for example. Over here, we have an example of someone pulling on a door. All right. You can pull on a door like this with a solid handle. You could also pull, excuse me, you could also pull on a box or something using a rope. Okay. And so we can push or pull in a variety of different ways, but most of the forces that we're going to deal with are going to be pushes and pulls. Okay. The other type of force that we're going to deal with is going to be friction. Right? If you've ever pushed a box or a refrigerator, for example, right, it doesn't just slide across the floor real easily. Okay? Sometimes things slide across a surface easily, and sometimes they don't. An example of something that slides across our surface easily is maybe a person on roller skates or a person on ice skates. Right? We give them a push, and they move pretty easily. Okay? And we say that the frictional force between the ice skater and the ice is small. All right? But let's say that we have a slab of concrete here, and we have, you know, a box here. It's made of wood. Well, we have a frictional force between the box and the concrete. And why do we have a frictional force? Well, even though it may look like the concrete is fairly smooth and the box is fairly smooth, there's a lot of nooks and crannies between the two surfaces. And they interact with each other, right? And they bump up against each other. right? And so we get this thing called a frictional force. And between an object like, or a surface like concrete, and an object like the box here, we get what's known as a coefficient of friction. And there are millions and millions of coefficients of friction between two different objects. Okay, and usually you'll be given the coefficient of friction, and the coefficient of friction is denoted by the letter mu here. All right, it's a Greek letter, looks like a U, all right, but we call it mu. Okay, the equation that we have for a frictional force is right here. The frictional force on a given object is equal to mu, the coefficient of friction, times something called the normal force of an object against the surface. Okay, we'll get into the normal force in a bit. Okay, but that's really all there is to it. How does a frictional force act? Well, a frictional force will always act in the opposite direction of the motion of an object. So let's say that I'm applying a force. It's actually already here. Let's say that the motion of the force is in this direction here. Okay, so I'm applying a force, I'm pushing to the right. What will be the direction of friction? It will be to the left. If I was pushing to the left, what would be the direction of friction? It would be to the right. Okay, so frictional forces will always, always, always go in the opposite direction of an applied force or motion. Okay, so that's friction. So I haven't really talked about what this normal force thing is. Well, remember that we talked about Newton's third law. All right, and Newton's third law is that for every action or force, there's an equal and opposite reaction. Well, let's say I have a table here. Here's my table, and I put a box on my table. I'll try to draw a nice box here. So there's my box sitting on the table. All right. Well, there's the force due to gravity on the box, right? And that force due to gravity is going to be pulling in the downward direction. Well, Newton's second law says that the sum of the forces on an object are equal to its mass times its acceleration. Well, the box is sitting on the table. It's not accelerating, right? However, there is a force, a gravitational force, acting on the box, right? There is that force due to gravity. So since it's not accelerating, there must be another force acting on the box, right, that is in the opposite direction, right, that basically cancels out the gravitational force, which gives us the zero acceleration. So the sum of the forces must equal zero here because we have no acceleration. Well, this force, and it's the force applied by the table surface on the box, is called the normal force. Okay, so we have a force due to gravity, right, due to the gravitational force of the Earth. But if the object is sitting on a surface, it can be a table, it can be the surface of the ground, it can be any surface, but it's got to be sitting on a surface, then there will be a normal force acting in the opposite direction. Okay, it'll be acting perpendicular to the surface of our object, and that's the normal force. Okay, so what we've done so far is we've covered Newton's three laws, right? Object will stay at rest. An object at rest will stay at rest. An object in motion will stay in motion unless acted on by some unbalanced force. Second law, the acceleration of an object is directly proportional, all right, to the sum of the forces on it, not just one force, right, but the sum of the forces acting on it, right? And remember that when we write our equation for the second law, we have to write an equation in the x dimension and in the y dimension if there are forces in each one of those dimensions. And then the third law is for every action or force, there's an equal and opposite reaction. Okay, we went through some examples, right? We talked about the forces, the types of forces that we're going to analyze. Gravity, pushes, pulls, and friction, essentially. And then we also introduced another force called the normal force. All right, and the normal force is due to an object sitting on a surface. Okay, so how then do we analyze these things? Well, first of all, before we discuss how we analyze them, we need to realize that all forces, every force, is a vector. Okay, what's a vector? A vector is something that has both a magnitude and a direction. Right? When I said I was pushing the car, I didn't say I was just pushing the car. I said I was pushing the car to the right or to the left. Right? So I gave it not just a magnitude. Right? The magnitude is the numeric part. Right? That's how much force I'm giving it. But I also gave it a direction. So it's very important that we understand that forces are vectors. Okay. Okay, so now that we realize that all forces are vectors and they have both a magnitude and a direction, what we want to do is we want to look at some steps to analyze a system of objects using Newton's laws. Okay. The first thing that we're going to do is we need to identify all of the objects in your system. Now, a system can have more than one object, as we'll find out. Okay. And as we encounter each of the objects in our system, and this will become more plain and more obvious as we do some problems, but I just wanted to give you the steps that we're going to use to solve these problems. We need to identify them. We need to identify, the second step would be to identify all of the label and identify all of the forces on each object. Because when we analyze a system using Newton's laws, we look at each and every object in the system as an individual thing, and we analyze that individually. Okay? Once we've analyzed everything individually and written equations for each object, then we can put it all together, as you'll see in a few minutes. Okay? So label every force on each object. And typically what we use is something called a free body diagram. Okay? And all a free body diagram is a diagram that labels and lists all of the forces that are on a particular object. 3, if the forces that are at an angle, okay, we cannot deal with them. Okay? We can only deal with forces that are either in the x dimension or the y dimension. So if they're at an angle, say like that, right? And let's see, here's our coordinate system here, right? And say this is 30 degrees. What I need to do is I need to break up this vector that's at an angle into an x component and a y component. And how do we do that? We use trigonometry to do that. Okay? So if we know the value of the vector up here, the hypotenuse, right? That would be the hypotenuse up here, and we know the angle, we can use trig to get the x component and the y component. And we're going to do lots of examples to show you how to do this. Okay. Number 4, write a set of equations using Newton's second law for each object in each dimension. Now, in many of the problems that we do, the forces are only going to be in one dimension. Okay? And so that makes it a little easier. But not all of the problems will have forces just in one dimension. Some will have forces in 2 dimensions, and we have to account for those. And then finally, we're going to solve the equations. All right? And we can have multiple equations, and when we have multiple equations, and so when we have those multiple equations, we're going to use multiple equations, put them together, and solve as simultaneous equations. Or we can do substitution as well. Whatever you feel most comfortable with. Okay. So those are the rules to solving problems. So this is the end of session 1. In session 2, what I'm going to do is I'm going to solve some basic problems, right? Show you how do we do free body diagrams, how we label problems, how we label forces, all right, and then actually solve the problems using Newton's second law. So I hope that helps. If it helps to watch this over again, please do that. But I know that watching problem solving is actually sometimes the most helpful thing. So watch part 2 and you'll see problems solved. And then there are also many other YouTube videos that I have where I've solved different types of problems. So I hope that helps, and have a great day.